Greetings. So today's class in embedded microcontrollers will continue with the microprocessor architecture. So already we have seen the paths like accumulator, and we have seen the flag registers, we have seen the program counter, the stack pointer, and in today's class we'll see about the timing and the control unit. So you can see in the diagram you have a timing and a control unit where you have some signals like read, write, ALE, ready, S0, S1, input output slash M bar, hold, acknowledge, reset in and reset out. To make it clear, I'll just tell you, ready is an incoming signal. Ready is a signal, you can see it is a signal which is coming inside from the external peripheral devices. Once the external devices are ready to accept or communicate with the processor, it produces a signal. Suppose it is slow and it is not ready, it makes this signal to go low, so the processor will go into a wait state. You can see some signals that's outgoing as read and write, so both are lower signals. These read and write work along with the IO slash M bar signal. So you will be getting around 4 control signals like input output read bar, input output write bar, memory read bar and memory write bar. So accordingly either the external devices or the memory will be selected for reading and writing. You have another signal called as the ALE. As we all know, this 8085 processor has got 16 address lines and 8 data lines. To reduce the number of pins, the low order address lines and the data lines are multiplexed together. So at the start of the clock cycle, this address lines, the addresses will be placed in the address lines and the ALE signal will be produced. So the address lines will act as a data lines. So what is ALE is? ALE is used to demultiplex the multiplexed address and the data lines. So this address lines will carry the data now. So that is the need for the address latch enable signal. You have another 2 signals like S0 and S1. These are status pins. This is outgoing pin and one can read the status of the processor, whether the processor is reading or executing or it is in the idle state. All these information can be arrived using the S0 and S1. You have another 2 signals like hold and hold acknowledge. These 2 signals are related with the DMA operation. What is DMA? DMA is direct memory access. DMA is used to transfer a bulk of data between the memory and the external devices without the intervention of the processor. So the processor will not be wasting its time. Instead, this DMA will take over the control of the processor and will make a bulk transfer of data between the memory and the external devices. So this is a signal that's coming from the DMA. Hold is a signal coming from the DMA requesting the control over the address and the data bus. So what the processor will do is, processor will say produce a signal as like hold acknowledge and give the control of the buses to the DMA. Next is reset in and reset out. These are produced by the processor to reset the devices along with the processor. So all the devices that's connected to the processor will be reset based on the signal. So this is what is a timing and a control unit. And the address and the data bus, the processor 8085 has got 16 address lines and 8 data lines. These 16 address lines are termed as A0 to A15, whereas the data lines are termed as D0 to D7. So these data and the address are multiplexed together. In another way, I can say as the data lines and the lower address lines are multiplexed together and they are termed as AD0 to AD7, as you can see in the diagram. So the processor will carry the address in one time, and after the ALE signal is produced, the same lines will carry the data. So this is what we say to reduce the number of pins or to use the pins effectively, some operations will have alternate function. So they will be multiplexed together and they can do one operation in one time and another operation in another time. Similarly, the address and the data lines are multiplexed together. The ALE signal will demultiplex or separate these two lines to carry the data lines, content. So you have another control logic which is called as an interrupt. So 8085 can have a control over can produce some interrupts too, can accept some interrupts too. So one interrupt is INTR, and other one is RST 5.5, 6.5 and 7.5. The last interrupt, which is the top priority interrupt, is the trap. So this trap has got the highest priority. The processor has no other go. The processor has to accept the interrupt coming through this pin and service the interrupt. And this processor has got some module as serial input output control unit. So there are two signals that is associated with this control unit. One signal is serial input data and another signal is serial output data. So serial input data is the pin through which the serial data will come inside, and serial output data is a pin through which the serial output data will move out serially. So one bit at a time the data will be transferred in and transferred out to the external devices as well as to the processor. You have another part which is called as the clock generator, as we saw in the timing and control unit. This processor works with a clock of about 3 to 5 megahertz. So these are the frequency. Based on the frequency, the time of execution or the synchronization will happen. So this is what is given. You can see two crystal frequency that is being connected internally so that it will produce a clock frequency. So now this is the architecture what we have completed. We have completed the whole architecture. The last class, earlier class and today's class we have completed the architecture. Now going with some simple assembly language programming, you can see one program is addition of two 8-bit numbers. So assume that we have two registers A and B and we are moving some data straight away or immediately to the accumulator as well as to another register B. So you have two instructions like MVI. MVI is moved immediate. So we are moving 25 to A and 15 to B, and we are adding so that B is added with A. It's implied, it means that add B means B should be added with A and the result is stored in A. Now the answer in the accumulator is saved in a memory location. So you have a stored accumulator 2050. And finally what you have is a halt. The next assembly language program is subtraction. We are subtracting 50 minus 30. So you can see we have moved A 50 and we have moved a value of 30 to B, and we have given an instruction as sub B. So 50 minus 30, you will have an answer of 20. That answer in the accumulator is moved back to the memory location 2051. So this is again, remember, each register are 8 bits, so you have 15, 30, all 8-bit numbers, and the memory location or the addresses or the memory address is about 16-bit. So you can see storing location is 16-bit. You have another instruction in another program as ones complement of a number. You can see a value of 55 is moved to accumulator and a complement is done. So what will happen? 55 will be converted to AA. Now that value is moved to the 20.